Right now, as you sit there watching this video, breathing in and out, your heart beating, your neurons firing, the atoms in your body holding together in perfect harmony. Something extraordinary is happening all around you. The empty space that surrounds you, the space between your fingers, the space between the Earth and the Moon, the vast stretches of nothingness between galaxies, that space is not empty. It has never been empty. And buried deep within the fabric of that so-called emptiness is a secret so terrifying, so profound, so mind-bending, that when physicists first discovered it, some of them literally lost sleep over it. Because what they found is this: the universe as we know it, everything you see, everything you touch, everything you love, every star, every planet, every atom, might be living on borrowed time. Not because of an asteroid, not because of a black hole swallowing us, not because the sun will die. No, something far worse. Something that attacks the very foundations of reality itself. Something that rewrites the laws of physics in an expanding sphere of absolute destruction. Moving at the speed of light, invisible, undetectable, and completely unstoppable. This is the story of vacuum decay, and today we are going to go deeper into this topic than you have ever gone before. We are going to start from the very beginning, from the most basic question you can ask: what is nothing? And we are going to build, layer by layer, concept by concept, all the way up to the most terrifying prediction in modern physics. Along the way, we will meet the brilliant minds who figured this out. We will understand the mathematics in simple terms. We will look at real experiments that have been done in laboratories, and we will answer the question that keeps cosmologists up at night. Can vacuum decay reach us? Is it already on its way? And if it is, would we ever know? Before we dive into any of that, I want you to do something for me. I want you to look around you. Look at the air between you and your screen. That air, or if you are in space, that vacuum, seems like nothing. It seems empty. But here is your first mind-bending fact of the day. According to modern physics, that emptiness is the busiest, most energetic, most complex thing in the entire universe. The vacuum of space is not a void. It is a seething ocean of energy, of invisible fields, of particles popping in and out of existence faster than you can blink. And the specific way those fields are configured right now, the specific energy level they sit at, determines everything about our universe. The mass of every particle, the strength of every force, the size of every atom, the way chemistry works, the way biology works, the way you exist, all of it depends on the vacuum being in one particular state. And here is the terrifying part. Physicists now have strong evidence, based on real measurements done at the Large Hadron Collider, that this particular state might not be the most stable one possible. Our vacuum might be sitting in a kind of temporary rest stop, a local minimum of energy, while somewhere in the landscape of possibilities there exists a deeper, more stable state. A true vacuum. And if our vacuum ever transitions to that true vacuum, even in one tiny spot, a bubble would form. That bubble would expand at the speed of light in all directions, and everything it touches would be fundamentally, permanently, and completely destroyed. Not destroyed like a bomb destroys a building, destroyed like erasing the rules of the game while the game is still being played. Atoms would cease to function. Chemistry would stop working. The forces that hold protons and neutrons together would change. Light itself would behave differently. And because the bubble moves at the speed of light, you would never see it coming. The light that would warn you about the bubble arrives at the exact same moment as the bubble itself. One moment you exist. The next moment, The laws of physics that allowed your existence have been rewritten, and you are gone. Not dead in any conventional sense, simply undefined, like a word in a language that no longer exists. Now, if that does not grab your attention, I do not know what will. But here is the thing. I am not going to just scare you with this concept. We are going to understand it. Really understand it. From the ground up. We are going to explore every angle, every detail, every twist. Because the story of vacuum decay is not just a story of cosmic horror. It is a story of the deepest physics we know. It connects to the Higgs boson, to quantum mechanics, to the Big Bang, to dark energy, to the multiverse, to the very question of why anything exists at all. It is one of those rare topics where the more you learn, the more astonished you become, not just at the danger, but at the sheer elegance and strangeness of the universe we live in. So if you are the kind of person who loves to go deep, who loves to understand the universe at its most fundamental level, you are in the right place. Hit that subscribe button, turn on the bell notification, because this is going to be a long, deep, and absolutely fascinating journey. Drop a comment right now telling me what you think empty space is made of. I will read through them after we are done. And smash that like button because this video represents months of research, and I want to share this knowledge with as many curious minds as possible. Let us start with the most basic question. What is a vacuum? In everyday language, a vacuum is simply a space with nothing in it. When you use a vacuum cleaner, you are sucking out the air, creating a region with less stuff in it. When we talk about outer space, we call it a vacuum because there are very few atoms out there, sometimes as few as 1 or 2 per cubic meter. So the common understanding is that vacuum equals emptiness, nothingness, the absence of everything. But in physics, this understanding is completely and fundamentally wrong. In physics, a vacuum does not mean a space with nothing in it. A vacuum means the lowest energy state of a system. It is the state you get when you have removed all the particles, all the radiation, all the excitations, and what remains is not nothing. What remains is the ground state of the quantum fields that fill all of space. And those quantum fields are always there. They never go away. They cannot be removed. They are as fundamental to the universe as space and time themselves. So what are these quantum fields? This is crucial to understand. In the early days of physics, scientists thought the universe was made of particles, little balls of matter bouncing around. Electrons were tiny spheres, photons were little packets of light, quarks were microscopic dots inside protons and neutrons. But as physics advanced through the 20th century, a completely different picture emerged. It turns out that particles are not the fundamental entities. Fields are. A quantum field is something that exists at every single point in space, at every single moment in time. It fills the entire universe. You cannot escape it. You are immersed in it right now. There is an electron field that fills all of space. There is a quark field. There is a photon field. There is a gluon field. For every type of particle we know, there is a corresponding field. And particles are not separate objects floating in these fields. Particles are the fields. More precisely, a particle is a localized excitation, a ripple, a vibration in its corresponding field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Think of it like the surface of a pond. The pond is the field. It exists everywhere. It is flat, smooth, quiet. That is the vacuum state, the lowest energy state of the field. Now throw a stone into the pond. The ripple that radiates outward, that is the particle. The ripple is not a separate thing from the pond. It is the pond, in an excited state. And when the ripple dissipates, the particle is gone, but the pond, the field, remains. This is quantum field theory, and it is the most successful framework in the history of physics. It has been tested to extraordinary precision. The predictions of quantum field theory match experimental results to more than 10 decimal places in some cases. It is the foundation of the standard model of particle physics, which describes every known fundamental particle and 3 of the 4 fundamental forces. And in this framework, the vacuum, the emptiness of space, is the state where all these fields sit at their lowest energy. No ripples, no excitations, no particles. Just the fields, humming quietly at their minimum energy. But even at this minimum, the fields are not completely still. This is where quantum mechanics comes in and makes things weird. You see, quantum mechanics has a rule called the Heisenberg uncertainty principle. This rule says that you can never know both the exact value of a field and its exact rate of change at the same time. There is always some minimum amount of fuzziness, some minimum amount of uncertainty. And this means that even in the vacuum state, the fields cannot sit perfectly still. They must jiggle, fluctuate, dance around their minimum value. These fluctuations are called zero-point energy, and they are real. They are not just mathematical abstractions. They have measurable, physical consequences. The most famous demonstration of zero-point energy is the Casimir effect. This was predicted by Dutch physicist Hendrik Casimir in 1948. He calculated that if you take 2 perfectly flat, perfectly parallel metal plates and place them very close together in a vacuum, they will experience a tiny but measurable attractive force. Not from gravity, not from electromagnetic charge, from the vacuum itself. The reason is that the quantum fluctuations of the electromagnetic field between the plates are restricted. Only certain wavelengths of the field can fit between the narrow gap, like only certain notes can resonate inside a pipe organ. But outside the plates, all wavelengths are allowed. This creates a pressure difference. There are more fluctuations pushing the plates together from the outside than pushing them apart from the inside, and the plates move together. This was experimentally confirmed by Steve Lamoureux in 1997 with remarkable precision. The vacuum pushed the plates. Nothing, literally nothing, created a measurable force. Think about that for a moment. The emptiness of space exerts a force on physical objects. This is how real quantum field theory's vacuum is. It is not nothing. It is something. It is a state, a configuration, a specific arrangement of quantum fields at their minimum energy. And that specific arrangement determines the properties of our universe. Now, here is where our story starts to get truly interesting. Among all the quantum fields that fill the universe, there is one that stands out as completely unique. It behaves differently from every other field. Its vacuum state is unlike any other. And it is this field that holds the key to the terrifying possibility of vacuum decay. This field is the Higgs field. You have probably heard of the Higgs boson, the so-called God particle, discovered at CERN in 2012. The Higgs boson is the particle, the ripple, the excitation of the Higgs field. But the Higgs field itself is far more important than the Higgs boson particle, because the Higgs field does something that no other known quantum field does. Its vacuum state, its lowest energy state, is not at zero. Every other quantum field we have discovered has a vacuum state at zero. The electromagnetic field's lowest energy is at a field value of 0. The electron field's lowest energy is at a field value of 0. But the Higgs field is different. The Higgs field's lowest energy is at a specific non-zero value, approximately 246 billion electron volts, or 246 GeV in physicists' shorthand. This means that even in the quietest, emptiest, most undisturbed region of space, the Higgs field is not zero. It is sitting at 246 GeV everywhere. All of space, every cubic centimeter, every cubic meter, every cubic light year is filled with this non-zero Higgs field. You are swimming in it right now. You cannot feel it, you cannot see it, but it is there, and it is doing something absolutely essential. It is giving mass to fundamental particles. Without the Higgs field sitting at its non-zero vacuum value, electrons would be massless. Quarks would be massless. The W and Z bosons that mediate the weak nuclear force would be massless. And if these particles were massless, the universe would be unrecognizable. Massless electrons could not be captured by atomic nuclei. Atoms could not form. Without atoms, there would be no molecules. Without molecules, no chemistry. Without chemistry, no biology. Without biology, no you. The non-zero value of the Higgs field is not just some technical detail. It is the reason you exist. It is the reason anything exists in the form we know it. The Higgs field's vacuum state, that specific value of 246 GeV, is the foundation upon which all of matter, all of chemistry, all of biology, all of human civilization is built. Now, to understand why this is both beautiful and terrifying, we need to understand the concept of an energy landscape. Imagine a hilly landscape, like a cross-section of a mountain range. There are peaks and valleys. In physics, every quantum field has an associated energy landscape, which physicists call a potential. The potential tells you how much energy the field has for every possible value it could take. If the field value is at the bottom of a valley in this landscape, the field is in a stable state. It will stay there, because any change in the field value would require climbing uphill, which costs energy. The lowest valley in the entire landscape is the true vacuum. It is the absolute minimum of energy. The field naturally wants to be there, and if it is there, it will stay there forever. That is the most stable state possible. But what if the landscape has more than one valley? What if there is a shallow valley and a deeper valley, separated by a hill? If the field is in the shallow valley, it is in a local minimum. It is stable against small disturbances, because any small push would not give it enough energy to get over the hill. But it is not in the deepest valley. There is a deeper state, a lower energy state, available. The field is in what physicists call a false vacuum. It looks like a vacuum. It behaves like a vacuum. It is stable for all practical purposes. But it is not the true vacuum. It is not the deepest possible minimum. And there exists, in principle, a way for the field to transition to the true vacuum. If it does, the consequences are catastrophic. The energy landscape of the Higgs field has a specific shape that physicists call the Mexican hat potential, or the sombrero potential, because it looks like a sombrero hat viewed from the side. In the center of the hat, at a field value of 0, there is a bump, a peak. This is a maximum of energy, an unstable point. If the Higgs field were at 0, any tiny disturbance would cause it to roll away. Around this central bump, the brim of the hat dips down into a circular valley. This valley is the minimum of energy, and it sits at a field value of 246 GeV. This is where the Higgs field currently resides. In the very early universe, when temperatures were extraordinarily high, the Higgs field had enough thermal energy to sit at the top of the bump, at zero. Everything was symmetric. All particles were massless. But as the universe cooled, about 1/1,000,000th of a second after the Big Bang, the Higgs field could no longer stay at the top. It rolled off the bump and settled into the valley on the brim of the hat. This is called electroweak symmetry breaking, and it was the moment that particles acquired mass. The specific point where the field landed on the brim, 246 GeV, determined the masses of all fundamental particles. If it had landed at a slightly different point, or if the shape of the hat was slightly different, particles would have different masses, forces would have different strengths, and the universe would be an entirely different place. Now, for decades, physicists assumed that the brim of this hat was the absolute lowest point, that there was nothing deeper, that the Higgs field at 246 GeV was the true vacuum, the most stable state possible. But then, something happened. Two things, actually. First, the theory of quantum corrections. You see, the shape of the Mexican hat is not fixed. It is affected by quantum effects. The quantum fluctuations of other fields, particularly the heaviest particles, feed energy back into the Higgs potential and change its shape. The Higgs-boson self-interaction tends to push the brim upward, curling it up, making it more stable. But the interactions with heavy particles, especially the top quark, pull the brim downward. The top quark is the heaviest known fundamental particle, with a mass of about 172 GeV. And because it interacts so strongly with the Higgs field, its quantum corrections are enormous. Whether the brim of the hat stays up or turns down depends on a delicate balance between the Higgs-boson's self-interaction pulling up and the top quark's interaction pulling down. And this balance depends critically on the precise masses of both particles. The second thing that happened was measurement. On July 4, 2012, CERN announced the discovery of the Higgs boson with a mass of approximately 125 GeV. This was a triumphant moment for physics. Decades of theoretical prediction confirmed by experiment. Peter Higgs wiped tears from his eyes. The physics world celebrated. But behind the celebration, a quiet concern rippled through the theoretical physics community, because 125 GeV was an uncomfortable number. Physicists had already calculated that if the Higgs mass were above about 130 GeV, the vacuum would be absolutely stable. The brim of the hat would stay up, and we would be in the true vacuum, safe forever. If the Higgs mass were below about 115 GeV, the vacuum would be completely unstable, and the universe as we see it could not exist. We would have already collapsed. But 125 GeV fell right in the middle, right in the zone that physicists called metastable. Stable enough to last a very long time, but not stable forever. The brim of the hat, according to the calculations, turns downward at very high field values, about 10 to the power of 12 GeV, 10 orders of magnitude above the current Higgs field value. And beyond that point, the potential keeps going down. There exists a deeper valley, a lower energy state, a true vacuum. And our current vacuum, the one that allows atoms and chemistry and biology and human beings, is not the lowest energy state. It is a false vacuum. Let me pause here and let that sink in. The measurement of the Higgs boson's mass, combined with the measurement of the top quark's mass, combined with the precision calculations of quantum field theory, leads to a startling conclusion: we probably live in a false vacuum. Our universe is metastable. The ground state of the Higgs field, the value of 246 GeV that gives particles their mass, and makes everything we know possible, is not the absolute minimum of energy. It is a local minimum, a temporary rest stop, a valley that is not the deepest. And somewhere in the landscape of possibilities, there is a deeper valley. A true vacuum. And the transition from false to true, if it ever happens, would be the most catastrophic event imaginable. Not just for us, for the laws of physics themselves. Now you might be wondering, if we are in a false vacuum, how exactly would the transition happen? Would the entire universe simultaneously shift to the true vacuum? Would there be some kind of cosmic snap? The answer is no. The transition does not happen everywhere at once. It happens through a process called bubble nucleation, and this is where the real physics gets absolutely fascinating. The theory of how a false vacuum decays was worked out by one of the most brilliant theoretical physicists of the 20th century, Sidney Coleman, at Harvard University. In 1977, Coleman published a landmark paper in the journal Physical Review D titled Fate of the False Vacuum, Semi-Classical Theory. This paper has been cited over 4,300 times and is one of the most important papers in the history of quantum field theory. In it, Coleman explained exactly how a false vacuum transitions to a true vacuum, and the mechanism is both elegant and terrifying. Remember the energy landscape with the shallow valley and the deep valley separated by a hill? In classical physics, the system is stuck in the shallow valley forever. It does not have enough energy to climb over the hill. But quantum mechanics changes everything. In quantum mechanics, there is a phenomenon called quantum tunneling. A quantum system can pass through an energy barrier even if it does not have enough energy to go over it. It is as if the ball in the shallow valley simply materializes on the other side of the hill, without ever actually climbing it. This is not science fiction. Quantum tunneling is a well-established, well-tested phenomenon. It happens every day in nature. Radioactive decay, the process by which unstable atomic nuclei emit particles and transform into different elements, is driven by quantum tunneling. The alpha particles inside a nucleus do not have enough energy to escape the nucleus's binding force, but they tunnel through the barrier and escape anyway. That is why radioactive materials emit radiation. Tunnel diodes, scanning tunneling microscopes, and even some biological processes rely on quantum tunneling. It is absolutely real. Now apply this to the Higgs field. The Higgs field is sitting in the shallow valley, the false vacuum, at 246 GeV. There is a hill, an energy barrier, separating it from the deeper valley, the true vacuum. Classically, the field is stuck. But quantum mechanically, it can tunnel. At some random point in space, at some random moment in time. A quantum fluctuation can cause a tiny region of the Higgs field to tunnel through the barrier and reach the true vacuum value. This creates a microscopic bubble. Inside the bubble, the Higgs field is at the true vacuum value. Outside the bubble, the Higgs field is still at the false vacuum value of 246 GeV. The bubble has a wall, a thin shell where the field transitions from one value to the other. This wall has surface tension, like the surface of a soap bubble, because there is energy associated with the transition region. Now, here is the critical question. Does the bubble grow or shrink? The answer depends on the bubble's size. The interior of the bubble is at lower energy, the true vacuum. So the bubble wants to expand. More volume at lower energy means less total energy. But the wall has surface tension, and that costs energy. The surface energy goes as the square of the radius, while the volume energy gain goes as the cube of the radius. For very small bubbles, the surface energy wins, and the bubble collapses. But there is a critical radius beyond which the volume energy gain exceeds the surface energy cost. If a bubble forms that is larger than this critical radius, the energy balance tips in favor of expansion, and the bubble starts to grow. And once it starts growing, it accelerates. The energy difference between the false vacuum outside and the true vacuum inside drives the wall outward faster and faster. Because the energy difference is typically enormous, the wall accelerates to nearly the speed of light almost immediately. And then the bubble expands, eating up the false vacuum and replacing it with the true vacuum, at nearly the speed of light, in all directions. This is vacuum decay. Coleman calculated the rate at which this tunneling process occurs. The formula is beautifully simple in structure, but involves an exponential suppression factor that makes the rate extraordinarily small. The tunneling rate per unit volume of space per unit time goes as the exponential of -b, where b is a quantity related to the energy barrier between the false and true vacuums. For large barriers, b is a huge number, and the exponential of a huge negative number is an incredibly tiny number. This means that for any given region of space, the probability of a bubble spontaneously forming in any given second is mind-bogglingly small. So small that the expected time for a bubble to form in a region the size of the observable universe is enormously greater than the current age of the universe. The most recent calculations, using the standard model parameters and including various corrections, give a vacuum lifetime of greater than 10 to the power of 65 years, with 95% confidence. Other calculations give even longer timescales, 10 to the power of 794 years per cubic gigaparsec of space. For reference, the current age of the universe is only about 1.38 times 10 to the 10th years. 13.8 billion years. The vacuum lifetime is so many orders of magnitude longer that the comparison is meaningless. It is like comparing the size of a single atom to the size of the entire observable universe, and then doing that comparison 100 times over. The probability of vacuum decay happening anytime soon through pure quantum tunneling is effectively zero. But there is a catch, and it is a big one. These calculations assume the standard model of particle physics is complete and correct. They assume there are no new particles, no new forces, no new physics beyond what we currently know. And we know, for certain, that the standard model is not complete. It does not include dark matter, which makes up about 27% of the universe's mass energy content. It does not include dark energy, which makes up about 68%. It does not incorporate gravity in a quantum mechanical way. It cannot explain why there is more matter than antimatter in the universe. It cannot explain neutrino masses. The standard model is extraordinarily successful, but it is incomplete. A new physics, whatever form it takes, could dramatically alter the stability calculation. It could make the vacuum more stable, pushing us into the absolutely stable region. Or it could make the vacuum less stable, bringing the timescale for decay much closer to the present. We simply do not know. The fact that the measured masses of the Higgs boson and top quark put us right on the boundary between stable and metastable is itself suggestive. As John Ellis of CERN has argued, the fact that we are living right on this knife's edge may be a hint that there is new physics beyond the standard model that stabilizes the vacuum. Perhaps supersymmetry, perhaps something else entirely. But until we find that new physics, the possibility of a metastable vacuum remains. Now, Let us go deeper into what Coleman and his colleague Frank de Lucía discovered when they added gravity to the picture. In 1980, Coleman and de Lucía published another landmark paper, Gravitational Effects on and of Vacuum Decay, in Physical Review D. This paper has been cited over 2,360 times. In it, they asked a natural question. What happens when you include the effects of general relativity, Einstein's theory of gravity, in the vacuum decay calculation? After all, the vacuum has energy, and energy curves spacetime. A bubble of true vacuum has different energy density than the surrounding false vacuum, so the geometry of spacetime inside the bubble will be different from outside. What are the consequences? The results were surprising, and in some ways even more terrifying than the original calculation. First, the good news. Gravity generally makes vacuum decay less likely. It stabilizes the false vacuum to some degree. The reason is subtle but beautiful. For a bubble to form, it needs to have zero total energy, because it materializes out of the vacuum, which has whatever energy it has. In flat spacetime without gravity, this is always achievable. You just make the bubble big enough so that the volume energy gain outweighs the surface energy cost. But in curved spacetime with gravity, the negative energy density of the true vacuum inside the bubble distorts the geometry. It curves spacetime inward, and this curvature limits the effective volume to surface ratio. For small enough energy differences between the false and true vacuums, there simply is no bubble with a large enough volume to surface ratio to have zero total energy. In that case, gravity completely prevents vacuum decay. The false vacuum is stabilized. This is actually reassuring. It means that some false vacuum states that would be unstable in flat spacetime are rendered permanently stable by gravity. But here is where the terrifying part comes in. Coleman and de Lucía found that within the bubble, the effects of gravity are dramatically different from what anyone had expected. The geometry of spacetime inside the bubble is not ordinary flat space. It is what physicists call anti-de Sitter space. Anti-de Sitter space has a negative cosmological constant, meaning the vacuum energy inside the bubble is negative. This type of spacetime has some remarkable mathematical properties. It has a specific symmetry group and is technically free of singularities. But it has a fatal flaw. Anti-de Sitter space is fundamentally unstable under small perturbations. Any tiny disturbance, any ripple, any fluctuation in the matter or energy content of the space triggers a gravitational collapse. Not a slow, gradual collapse. A violent, rapid implosion. Like the end state of a contracting universe, a big crunch, but happening on a microscopic timescale. Coleman and de Lucía calculated that the time required for the collapse of the interior universe is on the order of microseconds or less. Microseconds, the bubble forms, the laws of physics change inside it, and then, before anything meaningful can happen, the interior collapses into a gravitational singularity. And this led Coleman and de Lucía to write one of the most hauntingly beautiful paragraphs in the history of physics. I want to share it with you because it captures the profound horror and strange poetry of what they discovered. They wrote, "The possibility that we are living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In the new vacuum there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. Nonetheless, one could always draw stoic comfort from the possibility that perhaps over time the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. Read that again. Let it sink in. Before Coleman and De Lucia's 1980 paper, one could at least hope that after vacuum decay, something interesting might emerge. A new universe with different physics, different structures, maybe even different forms of life adapted to the new constants. But once you include gravity, that hope vanishes. The interior of the bubble does not evolve into a new, interesting universe. It collapses into a singularity in microseconds. Not only is our universe destroyed, nothing can take its place. The new vacuum is not just different, it is violently unstable. It does not persist long enough for anything, absolutely anything, to happen within it. Now I should note that this is the worst-case scenario. Not all vacuum decay scenarios are this extreme. The severity depends on the energy difference between the false and true vacuums, and on the specific properties of the true vacuum. Some scenarios are milder. A 1991 paper by Krohn and Scher investigated the environmental impact of vacuum decay and found that some vacuum transitions are actually compatible with the survival of large-scale structures like galaxies and stars, and possibly even biological life, depending on how the fundamental constants change. Other scenarios involve a transition to a vacuum with larger neutrino masses, which might have happened as recently as a few billion years ago. Another scenario involves decay to a vacuum with no dark energy, which would stop the acceleration of the universe's expansion but might not immediately destroy matter. There is even a scenario where the decay reduces the vacuum expectation value of the Higgs field, which would destabilize protons but might take a long time to actually disassemble all matter. So the consequences of vacuum decay span a wide range, from the subtle to the absolutely catastrophic, depending on the details. However, when physicists calculate what would happen specifically for the electroweak vacuum decay, the transition of the Higgs field from its current value to the true vacuum predicted by the standard model, the picture is grim. The true vacuum involves the Higgs field at a vastly higher value, and the resulting changes to particle masses and force strengths are so extreme that atoms cannot exist in the new vacuum. Electrons would become enormously heavier or lighter, depending on the specifics. The precise balance between electromagnetic forces and quantum effects that allows electron clouds to form stable shells around nuclei would be destroyed. Chemical bonds could not form. Molecules would be impossible. And without molecules, there is no chemistry, no biology, no life, no structure of any kind that resembles what we know. Everything inside the bubble would be rendered into a state of matter, or rather a state of non-matter, that has no analog in our experience. It would be like trying to run a computer program on a machine whose processor has been replaced with something completely different. The program is not just corrupted, it is meaningless. The instructions do not correspond to anything the new hardware can execute. Part 2, let me now paint a vivid picture of what it would look like, or rather what it would not look like, if a vacuum decay bubble were heading toward Earth. You are going about your day, nothing unusual. The sun is shining, birds are singing, people are commuting, working, laughing, arguing, living, somewhere, billions of light years away, or perhaps much closer. A bubble of true vacuum has formed. Maybe it formed 1 billion years ago. Maybe it formed yesterday. It does not matter, because the bubble has been expanding at nearly the speed of light ever since it formed. The wall of the bubble is thinner than an atom, a sharp boundary between two fundamentally different versions of reality. On one side, our universe, with our physics, our atoms, our chemistry. On the other side, a universe governed by completely different rules. rules that do not permit atoms, rules that do not permit light as we know it, rules that do not permit existence as we understand it. The bubble races across space, swallowing everything in its path. Stars, planets, galaxies, all consumed. Everything inside the bubble is instantly converted, not destroyed in the usual sense. Converted, transitioned, the fundamental fabric of space-time itself is rewritten. And here is the truly chilling part: you cannot see it coming. The bubble wall moves at nearly the speed of light. Light is the fastest possible signal in the universe. Nothing can travel faster than light in vacuum. So any light that the bubble might emit, any electromagnetic signal, any gravitational wave, moves at the same speed as the bubble wall. The signal and the destruction arrive at the same time. One moment, everything is normal. The next moment, the bubble wall passes through you, through the Earth, through the solar system, and everything is different. You do not feel pain, because pain requires a functioning nervous system, and nervous systems require atoms, and atoms require the old vacuum. You do not even have time to realize what has happened, because realization requires neural activity, and neural activity requires electrons in their proper orbitals, and those orbitals no longer exist. It is not death. Death implies a transition from living to non-living within the same laws of physics. This is something far more absolute. It is the end of the very framework in which concepts like life and death have meaning. Now let us talk about something that researchers have been exploring very recently, something that adds a remarkable twist to this story. In January 2025, a group of scientists published a groundbreaking paper titled "The Signals of Doomsday: False Higgs Vacuum Decay Signatures." This paper asked a question that previous researchers had not fully explored. What if the bubble wall does not move at exactly the speed of light? What if interaction with the surrounding medium, the gas, dust, plasma, and radiation that fills intergalactic and interstellar space creates friction that slows the wall down, even by a tiny amount? If the wall moves at even slightly less than the speed of light, then signals produced by the wall, specifically photons and neutrinos created by particle interactions at the wall, could outrun it, and those signals would reach us before the wall does. We would get a warning, not a long warning, not enough to do anything about it, but a warning nonetheless. The paper's calculations are remarkable. They found that the bubble wall interacts with matter through a process called vacuum mismatch. When the wall passes through space, the Higgs field abruptly changes from the false vacuum value to the true vacuum value. This sudden change creates Higgs boson excitations, particles of the Higgs field popping into existence at the wall. These Higgs bosons are unstable. They decay almost immediately, within about 10 to the power of -22 seconds, into other standard model particles. Since the Higgs is electrically neutral, it decays into equal numbers of particles and antiparticles, quarks and antiquarks, leptons and antileptons, bosons and antibosons. After these particles undergo further decays, hadronization, and matter-antimatter annihilation, the final products are predominantly photons and neutrinos. These are the messengers. They carry no electric charge, so they are not deflected by magnetic fields. Photons travel at the speed of light, and neutrinos travel at nearly the speed of light. They stream outward from the bubble wall in all directions. In addition to this vacuum mismatch channel, the paper found a second, even more powerful source of signal particles: thermal production from friction. As the bubble wall plows through the surrounding medium, friction dissipates energy, which heats the region around the wall to extreme temperatures. This thermal energy generates a continuous flow of Higgs particles and other particles, which again decay into photons and neutrinos. This thermal channel can produce many orders of magnitude more particles than the mismatch channel, and it continues operating even after the mismatch channel shuts down. Now, how much warning would we actually get? The paper calculated a specific scenario. Imagine a bubble forming 1 million light-years away from us. That is roughly the distance to the Andromeda Galaxy, our nearest large galactic neighbor. If the bubble wall slows by just 11 kilometers per second due to friction with the intergalactic medium, the photon and neutrino signals from the wall would reach us approximately 3 years before the wall itself. 3 years. Not enough to develop technology to stop it, but enough to detect it, enough to know it is coming. The signal would appear as a sudden, intense burst of high-energy neutrinos and gamma-ray photons coming from a specific direction in the sky. It would be unlike anything we have ever detected before. Our neutrino observatories, facilities like IceCube at the South Pole and the planned KM3 net in the Mediterranean Sea, would pick up the neutrino signal. Our gamma-ray telescopes, like the Fermi Gamma-Ray Space Telescope, would detect the photon signal. The signal would intensify as the bubble approached, growing brighter and more energetic. And then, at the speed of light, the wall would arrive and everything would change. This paper is remarkable because it transforms vacuum decay from a purely abstract theoretical concern into something that could, in principle, be observationally detected. It gives us a way, however limited, to look for vacuum decay happening elsewhere in the universe. And it opens up the question, if we ever detected such a signal, what would it mean? What would humanity do? How would we spend those last 3 years knowing that the laws of physics were about to be rewritten and there was absolutely nothing we could do to stop it? These are questions that venture beyond physics into philosophy, into ethics, into the deepest questions of human meaning. But they are questions rooted in real, calculable physics, and that is what makes them so powerful. Let me now take you back to the triggers. We discussed quantum tunneling as the spontaneous mechanism for vacuum decay, and we saw that the probability is so small as to be essentially zero on any human timescale. But are there other triggers? Things that could speed up the process, catalyze the transition, make vacuum decay happen much sooner than the astronomically long timescale predicted by pure tunneling? The answer is yes, and the most important catalysts are black holes. In 2015, physicists Berda, Gregory and Moss published a paper that sent shockwaves through the theoretical physics community. They showed that black holes could serve as nucleation seeds for vacuum decay. Near a black hole, the curvature of space-time is extreme. The gravitational field is so strong that it distorts the energy landscape of the Higgs field. This distortion can effectively lower the energy barrier between the false vacuum and the true vacuum, making it much easier for a bubble of true vacuum to form. It is like a scratch on the inside of a glass of superheated water. The scratch provides a nucleation point, a place where the phase transition can begin more easily. Black holes provide nucleation points for vacuum decay, and the paper found that the enhancement of the decay rate near black holes could be enormous. For certain black hole masses and certain values of the Higgs potential parameters, the catalytic effect is so strong that vacuum decay could happen within the current lifetime of the universe, rather than the astronomically long timescale predicted by random tunneling. Primordial black holes. hypothetical black holes formed in the extreme conditions of the very early universe, are particularly concerning. If they exist with the right masses, they could be triggering vacuum decay right now, somewhere in the universe. But before you panic, let me give you the crucial safety argument. If primordial black holes could efficiently catalyze vacuum decay, they should have done so already. The universe is 13.8 billion years old. Primordial black holes, if they exist, were formed within the first second after the Big Bang. They have had 13.8 billion years to trigger vacuum decay. The fact that the universe still exists, the fact that the vacuum has not decayed, is itself powerful evidence that either primordial black holes do not exist in the dangerous mass range, or they cannot catalyze vacuum decay as efficiently as the worst-case calculations suggest. This is a compelling argument. The universe is its own experiment. It has been running for 13.8 billion years, with all possible natural catalysts present, cosmic ray collisions at extreme energies, black hole formations and mergers, neutron-star collisions, supernovae, gamma-ray bursts. None of these have triggered vacuum decay. That is a very encouraging data point. Further research has refined the picture. A 2017 study found that in some scenarios, the true vacuum bubble does not expand outward from the black hole. Instead, it collapses inward into the black hole, or it pinches off and forms a separate baby universe that disconnects from our space-time. Either way, the bubble does not expand to consume the surrounding false vacuum. Our universe is protected. Even more encouraging, a 2019 study found that rapidly spinning black holes, which is the majority of astrophysical black holes, actually stabilize the false vacuum. They reduce the decay rate below what you would expect in empty space. Only small, slowly rotating black holes could potentially enhance the rate, and even then, the enhancement depends sensitively on parameters we do not know precisely. There is another speculative but fascinating trigger scenario that emerged in 2021. Rostislav Konoplik and his colleagues proposed that the region between two large black holes about to collide could create conditions favorable for true vacuum bubble formation. In this region, the space-time curvature is extreme and rapidly changing. Bubbles of true vacuum might form, and where the surfaces of these bubbles intersect, the energy density could become so high that micro-black holes form. These micro-black holes would then evaporate through Hawking radiation within about 10 milliseconds, before the larger black holes merge and swallow everything. The interesting thing about this proposal is that it is testable. The Hawking radiation emitted during this process would produce a characteristic signal that gravitational wave observatories like LIGO, Virgo, and CAGRA could potentially detect. If such signals were found in gravitational wave data, it would be evidence that vacuum bubble nucleation is actually occurring in the universe, albeit on microscopic scales near colliding black holes. So far, no such signals have been detected, but the search is ongoing. Another class of potential catalysts is topological defects, exotic structures that may have formed during phase transitions in the early universe. Cosmic strings, for example, are hypothetical one-dimensional objects, infinitely long or forming closed loops, with enormous energy density. They are like cracks in the fabric of space-time, relics of a symmetry breaking process in the early universe. In 2020, Firuzjahi published a paper showing that cosmic strings can act as catalyzers for vacuum decay, enhancing the nucleation rate compared to what you would get in empty flat space. The cosmic string provides a local distortion of the energy landscape. similar to how a black hole does, but with different geometry. And in very recent work from 2026, Chattarjian and colleagues investigated this further, finding specific gravitational wave signatures that catalyzed vacuum decay near cosmic strings would produce. Magnetic monopolies, another type of hypothetical topological defect, could similarly enhance the vacuum decay rate. However, cosmic strings and magnetic monopolies have never been observed. Their existence is purely theoretical. So while they represent an interesting possibility, there is currently no evidence that they are contributing to vacuum decay in our universe. Now, let us address the elephant in the room. The question that dominated news headlines when the Large Hadron Collider was being built. Could a particle accelerator trigger vacuum decay? Could humans accidentally destroy the universe by smashing particles together? When the LHC was being proposed and constructed in the early 2000s, this concern was raised by various people, including some who were scientifically literate enough to articulate the argument clearly. The reasoning goes like this. If particle collisions at high enough energies can create mini black holes, and if black holes can catalyze vacuum decay, then perhaps the LHC could create a mini black hole that seeds a true vacuum bubble, which then expands to consume the Earth, the solar system, the galaxy, and eventually the entire universe. Lawsuits were actually filed attempting to stop the LHC from being turned on. News stories with alarming headlines proliferated. The public was genuinely frightened. CERN took these concerns seriously and commissioned 2 independent safety assessments. The first, in 2003, and the second, by the LHC Safety Assessment Group, in 2008. Both concluded unequivocally that the LHC poses no danger. The reasoning is straightforward and compelling, and it relies on a single powerful observation: cosmic rays. Cosmic rays are high-energy particles, mainly protons, that travel through the universe at enormous speeds. They come from supernovae, active galactic nuclei, and other extreme astrophysical environments. When these cosmic ray particles slam into atoms in the Earth's atmosphere, or on the surface of the Moon, or on any planet, they produce collisions at energies far, far greater than anything the Lech can achieve. The Lech reaches collision energies of about 8 trillion electron volts. 8 tera electron volts. Cosmic rays have been observed at energies exceeding 5 times 10 to the 19th electron volts. The so-called Greisen-Zatsepin-Kuzmin limit. That is more than 6 million times more energetic than the LHC. And cosmic ray collisions at these extreme energies have been happening continuously everywhere in the universe for billions of years. Every planet, every star, every moon, every asteroid has been bombarded by cosmic rays more energetic than the LHC's collisions for the entire 13.8 billion year history of the universe. If high-energy particle collisions could trigger vacuum decay, it would have happened already. Not once, but trillions upon trillions of times. The fact that the universe still exists is absolute proof that particle collisions at LHC energies, and far beyond, cannot trigger vacuum decay. The universe itself has been running this experiment for 13.8 billion years, and the result is clear. High-energy particle collisions do not trigger vacuum decay. Furthermore, the energy required to directly push the Higgs field over the energy barrier is enormous, many orders of magnitude larger than anything achievable by any particle accelerator, present or foreseeable. The energy density needed is comparable to the Planck energy density, which is roughly 10 to the power of 114 joules per cubic meter. For comparison, the energy density in an LHC collision is roughly 10 to the power of 35 joules per cubic meter. That is a difference of nearly 80 orders of magnitude. It is like comparing the energy output of a firefly to the energy output of every star in the observable universe combined. There is simply no way for a human-made device to generate the conditions necessary to directly trigger vacuum decay. Physicist John Leslie calculated that particle accelerators will not match the energies of the most extreme cosmic ray collisions until approximately the year 2150. And even then, cosmic rays at those energies have been hitting the moon and other bodies for billions of years without triggering anything. The LHC scare was unfounded, and any similar fears about future particle accelerators are equally unfounded for the same reasons. Now I want to take you somewhere truly exciting. To the laboratory. Because in the last few years, something remarkable has happened. Physicists have actually observed false vacuum decay in the laboratory. Not the cosmic vacuum, of course, not the Higgs field, but analogous systems. Systems that obey the same mathematical equations as the cosmic vacuum, where the physics of bubble nucleation can be directly studied and tested. And what they found confirms the theoretical predictions with stunning accuracy. The most significant experiment was published in 2024 in Nature Physics by a team led by Andrea Zenassini. They used a system of ultra-cold atoms cooled to temperatures just billionths of a degree above absolute zero, forming a quantum fluid called a ferromagnetic superfluid. In this system, the atoms can exist in two different magnetic states, which play the role of the false vacuum and the true vacuum. By carefully tuning the system with lasers and magnetic fields, the researchers created a situation where one magnetic state was the false vacuum, a metastable state, and the other was the true vacuum, the more stable state. And then they watched. They watched as tiny bubbles of the true vacuum state spontaneously formed within the false vacuum fluid. These bubbles appeared at random locations, grew, and eventually consumed the surrounding false vacuum. Exactly as Coleman's theory predicted. The bubble nucleation process, the same process that could destroy the universe, was observed directly in a laboratory for the first time. Let me be very clear about what this means and what it does not mean. This experiment did not put the universe at risk. The energy scales are completely different. The atoms in the experiment are at nanokelvin temperatures, while the cosmic Higgs field involves energies of trillions of electron volts. What the experiment did was validate the mathematical framework. The same equations that Coleman wrote down in 1977 to describe cosmic vacuum decay also describe bubble nucleation in ultra-cold atomic systems. And when those equations were tested against experiment, they worked. The bubbles formed at the rate the theory predicted. They had the size the theory predicted. They grew in the way the theory predicted. This gives physicists enormously increased confidence that the theoretical calculations about the cosmic vacuum are correct. If the math works for ultra-cold atoms, and if the same math applies to the Higgs field, then the conclusions about the metastability of our vacuum are likely correct too. This was not the only experiment. In 2024, Jenkins and colleagues published a paper in Physical Review A describing generalized cold atom simulators for vacuum decay. These are purpose-built experimental systems designed to mimic the conditions of relativistic vacuum decay as closely as possible. They address technical challenges like edge nucleation, where bubbles preferentially form at the boundaries of the experimental system rather than in the bulk, which would contaminate the results. By eliminating edge effects, they created cleaner analogues of the cosmic process. Also in 2025, researchers used quantum computers to simulate false vacuum decay, using the computational power of quantum mechanics itself to model the process. The results again matched the theoretical predictions. And in 2026, another advance was reported, a tabletop experiment using a ring of Rydberg atoms, highly excited atoms with exaggerated quantum properties, that brought the universe's doomsday vacuum decay into the laboratory with unprecedented precision. These experiments are not just academic curiosities. They are building a comprehensive experimental foundation for understanding vacuum decay. Each experiment tests a different aspect of the theory: the nucleation rate, the critical bubble size, the dynamics of bubble growth, the interaction between bubble walls and surrounding matter. And each experiment confirms the theory. This is remarkable. We are talking about a cosmic process, something that, if it happens, would destroy the universe, and we can study it on a tabletop with ultra-cold atoms and lasers. The universality of physics, the fact that the same mathematical laws govern phenomena across vastly different scales, is one of the most beautiful and powerful aspects of science. Let me now broaden our perspective and connect vacuum decay to some of the biggest questions in cosmology. Because vacuum decay is not just a theoretical curiosity. It may be intimately connected to the origin of our universe, to the mystery of dark energy, and to the possibility of a multiverse. Let us start with the Big Bang. What caused the Big Bang? This is one of the deepest questions in all of science, and there is no definitive answer. But one of the most influential ideas in modern cosmology is cosmic inflation, proposed by Alan Guth in 1981. Guth suggested that in the very first fraction of a second after whatever happened at the very beginning, the universe underwent an extraordinarily rapid expansion. In a tiny fraction of a second, space expanded by a factor of at least 10 to the power of 26. This expansion was driven by a field called the inflaton, which was in a high-energy state, a false vacuum. The enormous energy density of this false vacuum caused space-time to expand exponentially fast, stretching out all irregularities and producing the remarkably uniform universe we observe today. And then, the false vacuum decayed. The inflaton field transitioned to its true vacuum state, and the energy that had been locked up in the false vacuum was released. This energy was converted into a hot, dense soup of particles, radiation, and heat, and that hot soup is what we call the Big Bang. So in a very real sense, vacuum decay may have already happened once. It may have been the event that created our universe. The Big Bang itself might have been a vacuum decay event, the transition of the inflaton field from a false vacuum to a true vacuum. The energy released in that transition became everything we see around us, every star, every galaxy, every atom, every person. We are living in the debris of a previous vacuum decay. This idea was refined by Andre Linde and, independently, by Andreas Albrecht and Paul Steinhardt into what is called slow-roll inflation or new inflation. In Guth's original model, the transition from false to true vacuum happened through violent bubble nucleation, which produced a highly non-uniform universe, in conflict with observations. Linde, Albrecht, and Steinhardt modified the picture so that instead of tunneling abruptly, the inflaton field slowly rolled down a gentle slope in its energy landscape, gradually transitioning to the true vacuum. This slow roll produced a much more uniform universe, consistent with what we observe. But the key insight remains: the early universe was in a false vacuum state, and the transition to the true vacuum is what made the Big Bang hot. And here is a mind-bending extension of this idea: eternal inflation. In the chaotic inflation model, different regions of the universe can be in different vacuum states. Some regions are still in the false vacuum, inflating exponentially. Others have already decayed to the true vacuum and formed what we would call universes. And the crucial insight is that the inflating regions grow faster than they decay. Even as some patches decay to true vacuum and form bubble universes, the remaining false vacuum expands so rapidly that there is always more false vacuum left over. The process never ends. Inflation is eternal. And each bubble universe has its own properties, its own physics, determined by the specific way it decayed. This is the multiverse. Not science fiction, not philosophy. A prediction of inflationary cosmology supported by the mathematics of vacuum decay. Our universe, with its specific physical constants, its specific particle masses, its specific forces, is one bubble in an infinite froth of bubble universes. Other bubbles have different constants, different masses, different forces. In some, atoms are impossible. In others, stars cannot form. In yet others, completely unimaginable forms of matter and energy exist, governed by physics we cannot even conceive of. And these bubbles are constantly being produced, popping into existence as patches of false vacuum decay, expanding into their own self-contained cosmic histories. The multiverse is vacuum decay writ large, happening everywhere, all the time, forever, now. If our universe was born from a vacuum decay event, and if our current vacuum is itself a false vacuum, then the cycle could continue. Our vacuum could decay, creating a new bubble with new physics. Our destruction could be another universe's birth. There is a strange kind of cosmic recycling happening, a constant churning of vacuum states, a never-ending process of creation and destruction at the most fundamental level. The universe is not static. It is not even just expanding. It is evolving at the level of its most basic properties, constantly testing new configurations, new vacuums, new versions of reality. And we happen to exist in one particular version, one that has lasted long enough for galaxies to form, for stars to ignite, for planets to coalesce, for chemistry to develop, for life to emerge, for intelligence to evolve, for you to sit here and watch this video and contemplate the nature of existence. The fact that we are here at all, in a universe that might be metastable, is itself a kind of miracle. In 2014, researchers at the Chinese Academy of Sciences in Wuhan provided an actual mathematical demonstration of something that had been proposed theoretically, that the universe could have been spontaneously created from nothing by quantum fluctuations of a metastable false vacuum. Nothing here means genuinely nothing. No space, no time, no matter, no energy, no laws of physics. A true void. And from this true void, a quantum fluctuation creates a tiny bubble of false vacuum. This bubble inflates, creating space and time as it goes. The false vacuum decays, releasing energy. The energy becomes particles. The particles form atoms. The atoms form stars and planets. And eventually, on one of those planets, a species evolves that can look up at the sky and ask, why is there something rather than nothing? The answer, according to this framework, is quantum mechanics. The void is unstable. Nothingness is not stable. Given enough time, which is a meaningless concept in the absence of time but still somehow applicable, quantum fluctuations will spontaneously create something from nothing. And the something that is created is a universe. Our universe. That is the deepest connection between vacuum decay and the question of existence itself. Let us now connect vacuum decay to one of the greatest mysteries in modern physics: dark energy. In 1998, two independent teams of astronomers made a startling discovery. By observing distant supernovae, they found that the expansion of the universe is not slowing down, as everyone expected. It is speeding up. The universe is accelerating. Something is pushing galaxies apart faster and faster. This mysterious something was named dark energy, and it constitutes about 68% of the total energy content of the universe. Despite being the dominant component of the cosmos, we have almost no idea what dark energy actually is. One leading candidate is vacuum energy, the energy of empty space itself, the zero-point energy of the quantum fields that fill the vacuum. If the vacuum has a small positive energy density, if empty space has a tiny but non-zero amount of energy per cubic meter, that energy would exert a negative pressure, pushing space apart, causing the expansion to accelerate. This is mathematically equivalent to what Einstein called the cosmological constant, a constant term in his equations of general relativity that he originally introduced and then famously called his greatest blunder. But the measurements of accelerating expansion brought the cosmological constant back. And here is the connection to vacuum decay. If our vacuum is a false vacuum, it naturally has a positive energy density. The energy of the false vacuum is higher than the energy of the true vacuum. That excess energy is the cosmological constant. That excess energy is dark energy. Dark energy might literally be the energy difference between our false vacuum and the true vacuum. If that is the case, then vacuum decay would not just change the constants of nature, it would also eliminate dark energy. The transition from false to true vacuum would bring the vacuum energy to zero, or to a negative value. The expansion of the universe would stop accelerating. And depending on the sign and magnitude of the new vacuum energy, the universe might start contracting, leading to a big crunch, or it might simply expand at a constant rate, or it might undergo some entirely different behavior. The current state of our universe, expanding with acceleration, is described by what physicists call de Sitter space, a spacetime with a positive cosmological constant. The true vacuum, if it has a negative cosmological constant, corresponds to anti-de Sitter space, the same unstable geometry that Coleman and Delucia showed leads to gravitational collapse. So vacuum decay would not just be a transition from one set of particle physics constants to another. It would be a transition from one geometry of space-time to another, from an expanding universe to a collapsing one, from de Sitter space to anti-de Sitter space, from a cosmos capable of supporting galaxies, stars, and life to one that implodes in microseconds. The connection between dark energy and vacuum decay is not just philosophical, it is mathematical, it is quantitative, and it is one of the most active areas of research in theoretical physics. Now, I mentioned earlier that the expansion of the universe could actually protect us from vacuum decay. Let me explain this in more detail, because it is one of the most fascinating and counterintuitive aspects of this entire story. The universe is expanding, not just the galaxies moving apart, but space itself stretching. And the expansion is accelerating, thanks to dark energy. This means that distant objects are receding from us faster and faster over time. And here is the key. Beyond a certain distance, called the cosmological horizon, objects are receding from us faster than the speed of light. Not because they are moving through space faster than light, which would violate relativity, but because the space between us and them is expanding faster than light can cross it. This is perfectly allowed by general relativity. The speed limit of light applies to objects moving through space, not to the expansion of space itself. The cosmological horizon is currently at a distance of about 46 billion light-years. Light emitted from beyond this horizon will never reach us, no matter how long we wait, because the space between us and that light is expanding too fast. Now think about what this means for vacuum decay. Suppose a bubble of true vacuum forms somewhere extremely far away, beyond our cosmological horizon. The bubble expands at the speed of light, eating up the false vacuum as it goes. But the space between us and the bubble is expanding faster than the speed of light. The bubble is growing at the speed of light, but the space it needs to cross is stretching even faster. The bubble is like a swimmer trying to cross a river, but the river keeps getting wider faster than the swimmer can move. The swimmer never reaches the other side. The bubble never reaches us. It is running on a cosmic treadmill, expanding furiously, but never making progress against the even more furious expansion of space. This is a genuine protective mechanism. If vacuum decay starts far enough away, the expansion of the universe ensures it can never reach us. The universe is, in a sense, quarantining the damage. The true vacuum bubble expands forever, consuming more and more space, but the false vacuum regions expand even faster, always staying ahead. This means that vacuum decay is only a threat if it starts close enough to us. How close? That depends on the details of the expansion rate and the bubble's speed. But roughly speaking, if the bubble forms within our Hubble volume, the region of the universe from which light emitted today could eventually reach us, then it is a threat. If it forms outside our Hubble volume, we are safe, not because the bubble stops, but because the expansion of space is an effective barrier that the bubble cannot overcome. This is a deeply strange situation. The same dark energy that might be a consequence of our false vacuum is also the mechanism that protects us from the consequences of vacuum decay in distant regions. The false vacuum is both the danger and the protection. It provides the energy that drives the expansion that shields us from the very decay that it is susceptible to. It is a cosmic feedback loop of extraordinary elegance. This brings us to the anthropic argument, and here we enter deep philosophical waters. In 2005, MIT physicist Max Tegmark and Oxford philosopher Nick Bostrom published a paper in the journal Nature examining global catastrophic risks, including vacuum decay. They pointed out something profound. We might systematically underestimate the probability of vacuum decay. The reason is observer selection. If vacuum decay happens in some region of the universe, everything in that region is destroyed, including any observers. The only observers who can exist, who can wonder about vacuum decay, who can calculate its probability, are those who happen to be in regions where vacuum decay has not yet occurred. We are, by definition, survivors. We exist precisely because vacuum decay has not happened in our region. But this does not mean vacuum decay is rare. It only means that we cannot be in a region where it has happened. There could be vast stretches of the universe that have already decayed. Vast regions where the true vacuum reigns and nothing we would recognize as matter or structure exists. We would never know, because we can only exist in the false vacuum regions. This is similar to the puddle analogy used by Douglas Adams, but inverted. A puddle might look at the hole it fills and marvel at how perfectly the hole fits it, concluding that the hole must have been designed for the puddle. In reality, the puddle fits the hole because it had no choice. Similarly, we might look at the stability of our vacuum and marvel at how fortunate we are. But in reality, we could only ever find ourselves in a stable or metastable vacuum, because we could not exist in a decayed one. The probability of vacuum decay could be much higher than our local experience suggests. Bubbles of true vacuum could be forming frequently throughout the universe. But we would never see them, because by the time we see them, it is too late. The light from the bubble reaches us at the same time as the bubble itself. We cannot observe our own destruction. We can only observe our continued existence. This is one of those arguments that seems to undermine itself the more you think about it. If we cannot observe vacuum decay, and if observer selection means we are biased toward thinking the vacuum is more stable than it might be, then how can we ever properly assess the risk? The answer is that we rely on indirect evidence, the mathematics of the Standard Model, the measured masses of the Higgs boson and top quark, the results of laboratory analogues, and the cosmic ray argument. All of these provide information that is not subject to observer selection bias. The mathematics of quantum field theory gives us a decay rate that does not depend on whether we are here to observe it. The cosmic ray argument tells us that extremely high energy collisions do not trigger vacuum decay, regardless of who is watching. And the laboratory experiments confirm that the mathematical framework is correct. So while the anthropic argument reminds us to be humble about our certainties, the actual evidence gives us substantial reason to believe that vacuum decay, while theoretically possible, is not an imminent threat. Let me now address a question that is both fascinating and slightly unsettling. Could an advanced civilization trigger vacuum decay deliberately? This is the stuff of science fiction, but it is also a legitimate question that physicists have considered. In a 2025 survey of experts on vacuum metastability, published on the Physics Preprint server, the average estimated probability that an arbitrarily advanced civilization could trigger vacuum decay was 18.8%. Not zero, not negligible. About 1 in 5. The reasoning is that while the energy densities required to push the Higgs field over the barrier are enormous, they are not infinite. A sufficiently advanced civilization, one that could harness the energy of entire stars or even entire galaxies, might conceivably concentrate enough energy in a small enough region to create conditions that catalyze the transition. They might do this by creating artificial micro-black holes, by engineering extreme gravitational fields, or by methods we cannot even imagine. The implications are chilling. If vacuum decay can be triggered by advanced technology, it becomes the ultimate weapon. A weapon that does not just destroy a planet or a star, but rewrites the laws of physics across an ever-expanding volume of the universe. A weapon from which there is no defense, no escape, no recovery. And a weapon that destroys the attacker along with everyone else, because the bubble expands outward from the point of creation in all directions. It is a mutual annihilation device of cosmic proportions, a weapon so devastating that its use guarantees the destruction of the user. This is reminiscent of the dark forest theory of the universe, popularized by Chinese science fiction author Liu Cixin. In the dark forest scenario, civilizations hide from each other in the vast emptiness of space, because any civilization that reveals itself risks being destroyed by a more advanced one. And the ultimate form of cosmic attack would be to trigger vacuum decay in the target's region of space. No defense is possible because the attack moves at the speed of light and changes the laws of physics themselves. Some have even speculated about a connection to the Fermi paradox, the famous question of why. In a universe with billions of potentially habitable planets, we have never detected any sign of extraterrestrial intelligence. One possible answer is that advanced civilizations inevitably discover the ability to trigger vacuum decay, and, sooner or later, some reckless or desperate member of such a civilization actually does it. The resulting bubble of true vacuum expands, eventually consuming everything within reach. Perhaps the reason the universe is so quiet is that advanced civilizations keep destroying themselves. and everything around them by playing with the most dangerous physics possible. This is speculative, of course, and there are many other proposed solutions to the Fermi paradox. But it illustrates how deeply vacuum decay connects to the biggest questions about our place in the cosmos. Let me now take a step back and address the question that has been hanging over this entire discussion. Should we worry? Should vacuum decay keep you up at night? Should you be anxious about the possibility that the laws of physics might be rewritten without warning? The answer, in my considered opinion, after researching this topic extensively, is no. And here is why. First, the numbers. The vacuum lifetime, calculated from the Standard Model, is staggeringly long, greater than 10 to the power of 65 years, and potentially as long as 10 to the power of 790 years. The universe is only about 10 to the power of 10 years old. The ratio of the vacuum lifetime to the current age of the universe is so enormous that it defies comprehension. You are more likely to shuffle a deck of cards and have it come out in perfect order, not once, but 1,000 times in a row, than to experience vacuum decay in the next trillion years. The probability is, for all practical purposes, 0. Second, the cosmic ray argument. Nature has been running particle collision experiments at energies far beyond anything we can achieve for 13.8 billion years. No vacuum decay has been triggered. This is not just a theoretical argument, it is an observational fact. The universe has stress-tested itself at extreme energies over enormous volumes for billions of years, and the vacuum has held. This is the strongest possible evidence that vacuum decay is not easy to trigger. Third, the possibility of new physics. The very fact that we sit on the boundary between stable and metastable may be telling us something. It may be a clue that there is new physics beyond the Standard Model that we have not yet discovered, and that this new physics stabilizes the vacuum. Supersymmetry, extra dimensions, or any of the many proposed extensions of the Standard Model could shift the calculation decisively into the stable region. Until we know the complete theory of particle physics, which we do not yet have, the metastability of the vacuum is not a settled conclusion. It is a prediction of an incomplete theory. Fourth, the expansion of the universe. Even if vacuum decay starts somewhere far away, the accelerating expansion of the universe provides a natural barrier. Bubbles forming beyond our cosmological horizon can never reach us. The universe is, in effect, self-quarantining. The very dark energy that might be a manifestation of our false vacuum is also the mechanism that limits the damage from vacuum decay. And fifth, perspective. There are many things that could end life on Earth, or even destroy the Earth entirely. Asteroid impacts, supernovae, gamma-ray bursts, the eventual death of the Sun. Compared to these very real, very well understood threats, vacuum decay is almost infinitely less probable. It is the least likely cosmic catastrophe by an enormous margin. Worrying about vacuum decay is like worrying about the ground disappearing beneath your feet while standing in the middle of a highway with cars coming. The cars are the real danger. The ground is fine. Focus on the cars. But while you should not worry, you should be fascinated. Because the story of vacuum decay is one of the most beautiful, most profound, and most intellectually rich stories in all of physics. It connects the smallest scales, the quantum fluctuations of fields, to the largest scales, the fate of the entire universe. It links the mass of a single elementary particle, the Higgs boson, to the question of whether the cosmos will exist forever or eventually destroy itself. It reveals that the emptiness of space is not empty at all, but is a complex, structured, potentially unstable state whose properties determine everything about the universe we inhabit. And it opens up mind-bending possibilities that our universe was born from the vacuum decay of a previous state, that the multiverse might be an infinite froth of decaying vacua, that dark energy might be the signature of our false vacuum, and that the ultimate fate of reality might be determined by the same quantum mechanical laws that govern the behavior of atoms and photons. Let me now share something that I find particularly beautiful about this story. It has to do with the relationship between creation and destruction. We tend to think of these as opposites. Creation is good, destruction is bad. But vacuum decay reveals that they are intimately connected. Our universe may have been created by the destruction of a previous vacuum state. The Big Bang may have been a vacuum decay event. The energy released by the transition from a false vacuum to a true vacuum may have produced all the matter and energy we see around us. Every star, every planet, every atom in your body may owe its existence to an ancient cosmic catastrophe, the decay of a previous vacuum. And if our current vacuum is also false, its eventual decay would not just be an ending, it would be a beginning. A new vacuum state, with new physics, new possibilities, new structures we cannot even imagine. The death of our universe could be the birth of another. Not a universe with life as we know it, perhaps, but a universe nonetheless. Something rather than nothing. Physics rather than void. This connects to the question asked by philosophers since ancient times: why is there something rather than nothing? The vacuum decay framework provides a possible answer: because nothing is unstable. The true void, the absolute absence of everything, is not a stable state in quantum mechanics. Quantum fluctuations spontaneously generate something from nothing. False vacuums inflate, decay, and produce universes. And this process may be eternal, without beginning or end. The cosmos is not a thing that was created at a specific moment. It is a process that is always happening, always churning out new versions of reality. Vacuum decay is not an aberration. It is the normal state of affairs. It is the mechanism by which the cosmos explores the landscape of possible physical realities. I want to share with you one more remarkable aspect of this story. It has to do with the precision required for our existence. The Higgs boson mass of 125 GeV and the top quark mass of about 172 GeV place us in the metastable region of the stability phase diagram. But just barely. The boundary between stability and metastability runs through the measured values with very little room to spare. If the Higgs boson were a few GeV heavier, we would be in the stable region, and vacuum decay would be impossible. If it were a few GeV lighter, the vacuum would be completely unstable, and the universe would have collapsed long ago. If the top quark were slightly lighter, we would be stable. If it were slightly heavier, we would be more deeply metastable. The values we measure are exquisitely fine-tuned to place us right on the edge. Why? Why should these values be so close to the boundary? There are several possible answers, none of them certain. One is the anthropic argument. Only universes where the vacuum is at least metastable can produce observers. If the vacuum is stable, that is fine, observers can exist. If the vacuum is metastable but long-lived, that is also fine, because the universe has had time for galaxies, stars, planets, and life to form before vacuum decay occurs. If the vacuum is unstable, no observers can exist, because the universe collapses too quickly. So by observer selection, we should expect to find ourselves in a universe where the vacuum is either stable or metastable. But we should not necessarily expect to find ourselves right on the boundary. The fact that we are so close to the boundary is genuinely puzzling and may be a clue to deeper physics. Another possibility is that the near criticality is dynamical, a consequence of some deeper principle that we do not yet understand. Perhaps the mechanism that set the Higgs and top quark masses was not random, but was guided by some principle that naturally produces values near the stability boundary. This idea is related to concepts like self-organized criticality, where complex systems naturally evolve toward critical states, or the principle of maximum entropy, or the asymptotic safety of quantum gravity. These are speculative ideas, but they suggest that the metastability of our vacuum might be telling us something profound about the fundamental laws of nature, something we have not yet understood. A third possibility, championed by John Ellis and others, is that the near criticality is simply a sign that new physics exists beyond the standard model and acts to stabilize the vacuum. In this view, the standard model's prediction of metastability is a consequence of the model being incomplete. When the missing physics is included, the vacuum becomes stable and the apparent fine-tuning disappears. This is perhaps the most exciting possibility because it means that the metastability of the vacuum is not just a curiosity but a guide, pointing us toward new discoveries. The next generation of particle accelerators, the proposed Future Circular Collider at CERN or the International Linear Collider, could provide the precision measurements of the Higgs boson and top quark masses needed to settle this question once and for all. More precise measurements could either confirm that we are metastable, or shift us into the stable region, or reveal the presence of new physics that changes the entire picture. Let us now revisit some of the specific scenarios for what could happen inside a vacuum decay bubble, because the range of possibilities is wider than most people realize, and some of them are genuinely surprising. The most dramatic scenario, the one I described earlier, involves a complete rewriting of the laws of physics. The Higgs field jumps to a vastly different value, particle masses change enormously, forces reconfigure, atoms disintegrate, and the interior geometry collapses to a singularity. This is the Coleman de Lucia worst case. But this is not the only possibility. Consider a scenario where the vacuum decay reduces the Higgs vacuum expectation value. In this case, the Higgs field transitions to a state where its non-zero value is smaller than 246 GeV, but still not zero. Particles still have mass, but different masses. Electrons are lighter or heavier. Protons and neutrons have different binding energies. Atoms might still form, but with different properties. The periodic table would be different. Some elements that are stable in our vacuum might be unstable in the new one, and vice versa. Chemistry would work differently. Biology, if it could exist at all, would take radically different forms. In this scenario, a paper by Turner and Wilczek showed that reducing the vacuum expectation value would destabilize protons. Proton decay, which in our vacuum is either impossible or happens on timescales far longer than the age of the universe, could become rapid in the new vacuum. Protons would fall apart, and all ordinary matter, which is made of protons and neutrons, would disintegrate. Not instantly, but on some timescale that depends on how much the vacuum expectation value changed. It might take milliseconds or it might take millions of years, but the end result is the same. No more atoms, no more chemistry, no more anything made of ordinary matter. Another scenario involves a change in neutrino mass. A 2019 paper by Lorenz, Funke, Calabrese, and Hannestad explored the possibility that the universe underwent a vacuum transition that changed the neutrino mass sometime in the recent cosmological past, within the last few billion years. This is a milder form of vacuum decay. Neutrinos are nearly massless in our current vacuum, but in the new vacuum, they might be heavier. Heavier neutrinos would affect the expansion of the universe, the formation of large-scale structures, and the cosmic microwave background. The authors found that current cosmological observations are actually consistent with such a transition having occurred. This does not mean it definitely happened, but it shows that some forms of vacuum decay might be subtle enough to have already occurred without immediately destroying everything. We might already be living in the aftermath of a vacuum transition, and we might not even know it. Yet another scenario involves the disappearance of dark energy. If the vacuum transitions to a state with zero cosmological constant, the acceleration of the universe's expansion would stop. The universe would continue to expand, but at a decreasing rate, asymptotically approaching a fixed size. This would not be immediately catastrophic. Galaxies, stars, planets, and life could continue to exist. The main difference would be cosmological. The far future of the universe would look different. Instead of all distant galaxies eventually disappearing beyond the cosmological horizon, they would remain visible. The cosmic microwave background would look slightly different. The ultimate fate of the universe would shift from a big freeze to something else. Perhaps a slow deceleration to a static state. This is the mildest form of vacuum decay, a cosmological nuisance rather than a catastrophe.